Hi, I'm Carlton Coffrin. This video is an archive of a presentation that I made at the IEEE PES General Meeting in 2018. The talk covers the annual meeting of the Task Force on Benchmarks for Validating Emerging Power System Algorithms. I'll begin with a brief overview of what we're going to cover in this video. The talk begins with a brief introduction of what the task force is all about, followed by some announcements of things that are going on in this space, a progress report of what we've been up to over the past year, and then we transition into proposed updates to the pglib OPF repository and review of the pglib OPF report draft for discussion at this meeting. I'll begin with a brief introduction of what this task force is all about. During the actual meeting, I gave a few slides that gave a brief overview of what we're trying to accomplish in this task force. For those of you who are viewing online, I would recommend you just watch these various YouTube videos, which provide a nice comprehensive overview of what the task force is all about. If you prefer to read, this activity page gives a brief overview of what we've been doing for the past couple years. Our primary activity thus far has been curating pglib-OPF, which is a repository of optimal power flow benchmarks. As of version 18.06, there were 36 base networks, 118 cases, all curated in the map power data format and provided under Creative Commons. This website provides detailed information about that repository and all the networks inside of it. So let's begin with some announcements. There have been ongoing recent developments in terms of power network datasets that are relevant to this particular task force. One of the very interesting things are the emergence of new grid repositories, so bettergrids.org and egriddata.org. Both of these came out of the IEEE Grid Data program, and they're now populated with a number of networks. So if you're looking for specific network data, I would recommend going and checking them out and seeing if something of interest is available to you there. Another activity has emerged, which has to do with this RTS GMLC update. So this is a revised version of the RTS 96 network that was being developed by NREL, and they've added a lot of additional information, especially about renewable resources possibilities for that network. They provided some basic geolocation of the network. It's a very enhanced data set, so I'd recommend checking it out if those type of things are of interest to you. Another exciting development that has to do with the IEEE Grid Data project is the release of a number of synthetic test cases. So there are at least 3 new notable archives of synthetic test cases. We have the Texas A&M University test cases, we have the Sustainable Data Evolution Technology test cases, and then also as part of a different project, the ARPA-E Grid Optimization Competition, there are new test cases being developed for that. So these are all very exciting sources of new network information that can be relevant to the efforts of this task force. I know, because I'm working on one of these grid data teams, that there are forthcoming real-world ACOPF cases that are based on the French system going to be released on this website at some time in the next year. So overall, I would highly recommend watching this space. There's a lot of new developments and new opportunities in the area of AC power network datasets. Another announcement I'll make is that I'll make a plea for curators of new datasets to be part of these different pglib repositories. I would love to see more benchmark curators working on different problem classes other than ACOPF. It's definitely within the scope of what we're trying to do here. So if you have your favorite problem, please contact me. I would love to see a proposal for next year's meeting. If you have a problem of interest, there are 3 easy steps to prepare it for this particular activity. First, you need to write down a mathematical specification of this favorite problem of yours. You need to encode some examples of this problem into a standard data format. And then once you've got that, you basically propose it at the next general meeting to this particular task force activity, and we discuss if it's appropriate for inclusion in these repositories. But please, I don't think it's a huge burden. If you're interested, please contact me. I hear from many people that there is a pressing need for a number of particular problems, benchmarks for a number of particular problems. These include things like unit commitment, stochastic optimal power flow, or three-phase optimal power flow. So if any of those things seem exciting to you, please let me know. So now we're on to the progress report part of the discussion. So what have we done in 2018, 2017, 2018? In August last year, we had the first official release of the PGlib OPF library. That was version 17.08. And so far, it has been doing quite well. If you look at the statistics on GitHub, we have 8 watchers, 11 stars, and 9 forks as of a few days ago. And we're seeing about 50 unique visitors in a given 2-week period. So there's lots of traffic going to the repositories. Minor updates were made to the repository in June, so that's version 18.06. There wasn't very significant changes. Basically, some transformer parameters were updated and some base KV values were changed in the IEEE 14 and 57 cases. These were really just minor changes based on some bugs that were observed over the past year. In the previous month, we've developed the OPF repository draft, the PGlib OPF repository report draft, so that's one of the topics for review at this meeting. And in this month as well, we have some proposed additions to the PGlib OPF repository, which was approved last year. So at the end of this talk, we'll be discussing version 18.08, which includes these new network additions. So what are our plans for 2018 and 2019? We're going to release the PGlib OPF repository report. We are also going to conduct routine maintenance on the PGlib OPF repository, and in accordance with the plea I made just a moment ago, we're looking for other problem classes to curate, like unit commitment, stochastic OPF, and three-phase OPF. I think ACOPF is in fairly good shape. We have quite a few test cases at this point with interesting challenges to be addressed, so it's a good time to look at more complicated problems. So that's the end of the progress report. Now we can move on to the Power Grid Library OPF updates. The main reason for these updates is that a lot of new networks are now available. So what I looked into were 3 new data sources: the Texas A&M University cases, these SDET cases, and then also cases available as part of the grid optimization competition. And I'll go through each of these and tell you about what my experience was trying to prepare these test cases for inclusion in this library. So the first thing, we'll start with the Texas A&M cases. These are synthetic cases with seemingly realistic parameters. They look fairly reasonable just by visual inspection. They have a very large range of sizes, so they go from just 200 buses to, say, 70,000 buses. I observed some numerical challenges in trying to get ACOPF feasible solutions on the larger cases. So I focused my attention just on these 200 to 10,000 node cases, all of which easily converged in an ACOPF baseline study. So those were the ones I focused on incorporating. When we look at the CDET cases, these are also synthetic cases with seemingly realistic parameters. They range from about 500 buses to almost 5,000 buses, and all of these cases appeared to be AC feasible without much trouble, so I left them mostly as they are and tried to incorporate all of them. Finally, the grid optimization competition cases. These, again, they seem synthetic, but the parameters seem to be fairly realistic. There was just some notes that this 179 bus system is based on an old, like 1994 study of the Western United States, but I haven't had time to look into a lot of the details to understand the level of realism there. For sure, 179 buses is would be a very aggregate version of the Western United States. So these are the 3 networks that have been considered for this particular collection. Already the 14 bus and 96 bus are included in this library, so the 179 bus is the one that's providing possibly new information, so we looked into incorporating that as well. So here are the 9 new networks that are proposed for the next version of this ACOPF repository using the standard naming conventions for this repository. Just to make sure everything was reasonable, I did a basic validation study. Here are the results of all those different cases under their kind of typical operating condition, and then congested operating condition and a small angle difference condition. These are all standard modifications that all the other test cases have gone under. So there's nothing particularly abnormal about all the different versions. The first thing I would note is that all of the cases, including the modified versions, have AC feasible solutions. If you look under this AC column, you'll see that there's a value for every one of the test cases, which indicates we were able to find an AC feasible solution, so that's good. There are definitely some interesting optimality gaps for these cases. So if you look, even in the base case, we're seeing some optimality gaps of, say, 5% or 2%. In the modified cases, we're seeing even bigger optimality gaps, which suggests these are useful for benchmarking ACOPF algorithms. There may be some interesting runtimes in the largest cases, like the 5,000 and the 10,000 node cases. So these look like they might also be a reasonable tool for testing scalability of algorithms as well. So just to highlight the changes from last year in going to this proposed new version, we're going from 36 to 45 networks that range between 3 and 13,000 buses. In 2017, this is what the breakdown of different networks looked like based on their original source, and now we're adding two major new sources, the Texas A&M cases and the CDET cases, and then also one case from this grid optimization competition. So this is what the new distribution looks like in 2018, and I'm glad that each piece of the pie now is getting kind of more even, because we're not particularly biased to one network or another. So that's the end of the update of the networks. At this point in the discussion, there were no objections in the room for updating the repository to this new version and incorporating these 9 new networks. Now we'll move on to the PGlib OPF report. So there is a report draft. I'm currently socializing it with different contributors of test cases to make sure that everyone's on board with what we're discussing. I won't go over this draft in particular detail, but I will give you kind of a sketch of the argument within the draft for if there's any discussion or comments or questions. So the basic report sketch is the following. We have our AC optimal power flow problem of interest that we're going to standardize around for benchmarking. We highlight that if we used the cases that are distributed with map power for this benchmarking exercise, it would not be particularly challenging, so it would not produce ideal results for comparing different algorithms. We'd conduct a survey of available networks and also highlight that some data is missing, like line thermal limits from those networks. Then we review some approaches to populating that missing data, and then combine it all together to build this baseline PGlib OPF repository and provide basic validation results to show that these are at least potentially interesting cases for benchmarking ACOPF algorithms. So what is the optimal power flow formulation that we're interested in? This is also available on the repository's README, but I'll quickly go through it now. We have a quadratic kind of fuel cost function which tries to minimize active power. We have box generation limits on all of the generators. We have thermal limits, or we have active power limits on the nodes, or voltage magnitude limits on the nodes. We have bus shunts incorporated into Kirchhoff's current law. We have transformers in the power flow equations, and also a line charging component in the power flow equations. And then finally, we have both a thermal limit on the branches and an angle limit between pairs of buses where branches exist. So for more detail of this model and its derivation, you can check out this archive paper. So this leads to another interesting question. If we have that particular mathematical model, what would make a good benchmark for that model? I don't know if there is a very clear answer to that question. It's a bit of a magic or an art, usually in optimization, picking good benchmarks. But we believe that a large optimality gap is a reasonable metric for what makes a hard ACOPF test case. Now, why is that? Well, if you have a large optimality gap, you can really only have two cases. Either you're really struggling to find the global optimal solution, so finding a feasible solution to the optimal, or finding the best solution of the power flow is very difficult, or you have the best solution but providing a lower bound to that solution and kind of proving it's the best solution is very difficult. So you can kind of have hardness of finding the solution, hardness of proving that it's optimal, but if they're both very close, it's kind of an easy problem. So that's why we think optimality gap is a useful metric for this. And so just to get our a basic litmus test of is a problem hard or easy for OPF benchmarking, we begin with an off-the-shelf non-convex heuristic solver. We're going to use IPOpt. If it converges to a feasible point, it gives you some locally optimal ACOPF solution. And then we're going to use a very simple convex relaxation based on a second-order cone program. This is one of the oldest relaxations, one of the easiest ones to implement. So it's really a very basic bar to pass that the optimality gap between these two approaches is significant. So if we look at the typical cases that that are distributed with MapPower, and we try to do a very simple test where we run the AC non-convex problem, and you solve it here as a heuristic, and then we run this convex second-order cone relaxation, what do we get? So the first thing you can observe here is that there are a number of cases where the optimality gap is less than 1%. This suggests that these cases are very easy. Both IPOpt is finding a near global optimal solution, and a very simple relaxation can prove that it's near globally optimal. You might also notice that the runtimes here are quite small, again suggesting that these problems are relatively easy. There is an interesting point about some of these problems, so like case 9 target and case 145 had no solution in the heuristic, the non-convex AC heuristic, and that could suggest that maybe a solution exists, but it's just hard to find, which would be nice. That would be a challenging test case. But unfortunately, the second-order cone program suggests that these problems are actually infeasible. So there's no way to assign a solution that can satisfy all of the constraints in the original ACOPF problem formulation. Now, this might be due to the fact that the problem data was not designed for ACOPF, and so in any case, this proof of infeasibility suggests that these aren't particularly hard problems either, because we can very easily prove that there's no solution. So this leads to a natural question: why are these cases so easy in general? And if you do a survey of where this different data sets come from and what of data was originally available, you find that a number of them are kind of missing key pieces of either generation capability limits, generator cost functions, or line thermal limits, which were all key pieces of an ACOPF formulation. In particular, many of the cases are missing this generator cost functions, which can have a huge implication on the optimality gap in your particular problem. It's worth noting that both the Pegase and the RTE cases have a cost function which is minimizing losses, but this is kind of like a special case of the more general quadratic cost function that the ACOPF can support, and it's a particularly easy case to solve as well. So what do we do in the report? We review a number of data models that have been proposed previously. For example, by taking the generators in the networks and trying to assign them a particular fuel cost. This is an empirical distribution based on the nameplate capacity of the generator, what particular fuel it's most likely to use. Using the fuel cost or the fuel type, you can then kind of guess what the fuel cost would be based on the price of different raw materials on the market. And this is all provided by EIA, which collects national U.S. energy information. And so these types of models are used, these and a few more, are used to basically populate all the missing data in those networks. So then we have this table which describes for each of the different networks what models were used to complete the missing data. This is just a subset of the table. So that leads to, these modifications lead to what we call the typical operating condition of the base case of the networks. We also add modified versions like active power increase and small angle difference variants of the network, just to have some more cases to test on. So with all of those different updated networks and model variants, we conduct a very preliminary baseline result just to check that these should be interesting for benchmarking ACOPF algorithms. We don't have time to go into all these in detail, but I'll just highlight a subset of the results. So if you look at the typical operating conditions, you'll already see that there are some non-trivial optimality gaps here. So just filling in the missing data on the base cases has resulted in some interesting cases that are particularly useful for benchmarking ACOPF algorithms. When you look at the modified cases, like the active power increase cases, you see even more dramatic increases in optimality gaps, again suggesting that these cases are particularly good for benchmarking ACOPF algorithms. So that summarizes the report draft, and as I mentioned, the detailed document is currently being distributed and reviewed by a number of contributors. So if you have any particular comments or concerns about what this has been presented, now is a good time to share those. So thank you very much for watching. We hope that you enjoy PGLib OPF, and if you have time, it would be great to see you at next year's meeting of the task force. Thank you very much.